Good morning, students. So here we are going to continue our the portions. We have already started with the second module, that is velocity and acceleration in mechanisms. So you already know that this method of finding velocity and acceleration in mechanisms can be done in two ways. One is graphical method, and another one is analytical method. So this graphical method is also known as relative velocity method. So we have already started this method for 4 bar chain, and we have completed two sums also. Now we'll move on to the next mechanism, that is slider crank mechanism. So here you can see a question, and I hope you know what is slider crank mechanism is. In slider crank mechanism you have got a crank which can rotate 360-degree and which is connected to connecting rod, and which is in turn connected to the piston. So when the crank rotates, the piston reciprocates, or it moves in a linear direction. So in all the slider crank mechanism, this rotating motion is converted into the linear motion. So we can just look into this question which is given over here. Here it is given that the crank of a slider crank mechanism rotates clockwise at a constant speed of 300 rpm. The crank length is 150 mm and connecting rod is 600 mm. Now what we have to find out, first question is we have to find out the linear velocity and acceleration of the midpoint of the connecting rod. Second question is finding out the angular velocity and angular acceleration of the connecting rod, and also it is given that crank angle is 45 degree from inner dead center position. So first and foremost thing is we need to draw the, hope you know that we have to draw the space diagram with actual measurements. Then using that we have to draw the velocity diagram, and we have to draw the acceleration diagram. So before that we should know what are the given data. So we'll move into that. Yes friends, now we can see the given data in the question. So it is given that the mechanism used here is a slider crank mechanism, which is already shown here, and we can see what is the speed at which the crank is rotating, that is 300 rpm, and the length of the crank and length of the connecting rod is also given. So this is the value. So it's very difficult to draw according to this value, that is this is 15 centimeter and this is 60 centimeter, so it will be very big. So what we'll do is we'll convert into scale. Okay, so hope you already know how to convert into scale. So what we are going to do here, it is the scale which we are doing is we are dividing the both value by 5, that is 15 centimeter also we are dividing by 5 and 60 also we are dividing by 5. So 1:5 will be the scale we are taking here. So the value becomes 3 for crank and the value becomes 12 for connecting rod. Yes, now you can see the scale which we are using is 1:5. Okay, now we'll start drawing the space diagram. Hope you already know. I'm not showing the detailed steps because you already know. Okay, so I'll just explain the steps. So first we'll draw any horizontal line of any length. Then at one end we'll mark the point A, and what we'll do is we will take the 45-degree line on that. Then we will take 3 centimeter in the compass and draw an arc, and you can get this point B. You can join this, you will get the point B. Now what we'll do is we'll keep compass here B as center, and the radius, this length is it is nothing but we have already found out there, here it is 12 centimeter. Okay, so B as center, 12 centimeter. You will draw an arc on this horizontal line to get this point C. Now you got this point C, you join this, you will get the required length of the connecting rod, and you can just mark a piston also over here of any length, no issues. Okay, so we have finished drawing the space diagram. Now from the space diagram we will draw the velocity diagram. Okay, so before drawing this velocity diagram we have a small calculation. So first of all we will take care of the speed of the crank, that is 300 rpm, it is given. Then the angular velocity of the crank is also given. We have to find out how we'll find out by 2 pi n of this value divided by 60. So we'll substitute that value, 2 pi into 300 by 60, you got it as 31.42 radian per second. So this is the angular velocity of crank AB. Now we have to find out the absolute velocity or the linear velocity of crank AB. Okay, so we will denote by VB given A. Since the point A is fixed, we can ignore that, we can simply write VB. This has already explained to you in the previous classes. So I'll just directly write down, which is equal to the link length R into the omega. Okay, so link length is since it is 15 centimeter or 150 mm, it is converted to meters, 0.15 into 31.42, which is equal to 4.713 meter per second. So this is the value with which we have to start drawing the velocity diagram. Now we'll come into the velocity diagram. Okay, so you know that first of all we need to mark any fixed point where all the fixed link is coming. You can see only A is the fixed link. There are no any other fixed links. So we'll start with the point A. Now from this point A, draw a line, okay, which is parallel to this direction. What is this direction? This is the direction of the velocity, and you know that velocity will be direction of velocity for a link will be always perpendicular to its link length. Okay, so this is the direction. We are getting this direction by keeping the protractor here, draw a 90 degree, so you got a perpendicular line, so you got this is the direction of the velocity of this link. Okay, now we have to draw the velocity. What is the value? We already got that. The value is, I'll show you the value, it is 4.713. so 4.713 you have to draw from here. In which direction? That is this direction. So using roller scale, you can roll and come over here, you'll get the direction, and to draw the length 4.713. So you will get this point B. Now what we'll do from here, we have to draw the velocity of this link BC. So here also we found out the direction, it is always perpendicular to the link. So that means you have to draw a line which is parallel to this direction, and from here, so you will keep the roller scale, roll it here, you got the direction and you don't know the magnitude, how much you have to draw. So what we'll do from here, draw a line in that direction, just keep on extending both sides. We don't know which direction we have to draw. Okay, now we'll keep it over there. Now we'll go for the next link. Next link is nothing but the piston. The piston, it is constrained to move only along this direction. So this is the direction in which the velocity of the piston can act. So that we have to represent here. So what we have to represent is, till now we have drawn this line and this line. Now we don't know the point C. So what we will do is, where we have to start? We have to start from point A, because the piston will be moving and meeting this point. Okay, so that is why we can start with the point A. So from this point A, draw a line which is in direction of this one, parallel to this direction. So we'll draw that line. So this line, if you join, you will meet it over here and you get the point C. So you can complete this diagram like this. So this is the required velocity diagram, and if you measure BC, you will get the value of VC given B. This is the vector BC. That is, measurement is around 3.4 you will get. So any values above plus or minus 0.5, it is okay. Okay, so you can take that value. It is 3.4 you are getting, and this velocity, this is nothing but the velocity of the piston. This is the velocity of the connecting rod. Okay, so velocity of the connecting rod is VC given B 3.4, and velocity of piston VC is nothing but 4. If you measure, you will get 4 meter per second. Now second part of the question, other part of the question is, you have to find out the velocity of a point which is at here, the midpoint of the connecting rod. Okay, so how to find out that is, see, we know that we have taken everything with respect to this velocity diagram with respect to the space diagram. So the ratios of the sides of both the diagrams will be same. Okay, that's why I'm simply I'm assuming a point here. Before that we don't know the point here. Okay, so I'm just simply assuming the point here, that is BD. That value, this BD value will be equal to will be divided by the total, this BD equal to BC. What is BC? This value divided by the total value BC. So that is BD by BD is equal to BC small bc by capital BC. So you take this on the other side, you will get like this. So we can substitute the values. Since this value we don't know initially, we know which all values we know this whole value we can measure. We got it as 3.4 divided by this full BC is 12. 12 is what we have taken in the scale. So divide by 12 into this BD. BD means this we can know this, since it is a midpoint. Total is 12. This will be 6. Okay. So that is how we have done. So we got the value 1.7. Okay. So what we can do is from here take 1.7 and mark a point here. So that will be your required small letter D. Okay. Now what we'll do is from here draw a line which is meeting using scale. You join AD, and so this and measure this one. So this will be the velocity of the midpoint of the connecting rod. So that is VD. You measure this, that is vector AD. So that is nothing but 4.5. So this is how you can find out the velocity of different points in a link. Okay. Now we'll start drawing the acceleration diagram. So for acceleration diagram also we require the space diagram. From space diagram only you are drawing the acceleration diagram. Now we can see before drawing the acceleration diagram, you should find out the radial component and tangential component of the different links. So first of all we'll see for the link AB. Link AB is a crank. So crank, what is the radial component? AR of B. So that is nothing but velocity of that link square divided by the link length. Velocity we already got that 4.713 square divided by the link length is 0.15. So we got the value 148.1 meter per second square. Now we'll think about the next link, that is connecting rod BC. Radial component radial component AR of C given B is equal to velocity square of that link divided by the link length. So that again we have put and got the value. So this is the value. So here we will not find out the tangential component since it is the crank, and crank can rotate 360 degree. So there is no tangential component, only radial component will be its acceleration. But you can have the tangential component for connecting rod, since the connecting rod is not having the complete 360 degree rotation. So you can have this, but in order to find out that you require angular acceleration, which is not given. So time being we'll just put it X question mark over there, and we'll proceed with the our drawing. So before drawing that, you can see you saw that the value of the radial component is 148 for crank, and the value of radial component of connecting rod is 19.3. So if you directly draw 148.1 centimeter and 19.3 centimeter, this will be very big. So again here also we'll convert into one scale. What I'm doing is dividing the both component by 20. So if I divide by 20, I'm getting 7.405 and 0.965 here. Okay. So I will start drawing the acceleration diagram. I will explain you how I have drawn this one. So what is the scale I'm doing? I told you I'm dividing by 20. So that means the scale 1 centimeter. How much I'm drawing? 1 centimeter. That means that is nothing but 20 meter per second square. So that is the scale I have to draw. This is very, very important. You have to mention the scale. So for acceleration diagram also, you have to start from the fixed point, like what you have done in the velocity diagram. So first of all, the fixed point is nothing but the point A, that here we will mention as A dash. Now first of all, we have to draw the acceleration of this link. In order to draw the acceleration of this link, we require the radial component. We will draw the radial component first and tangential component. Since you know that we don't have tangential component here, since this is the crank, So only radial component is enough. So in order to draw that direction, it is along the link length, and the direction we have to take downward direction because radial component always acts towards the center. So downward direction we'll take. So that is what we have done here. From here, draw a line which is parallel to this direction. Okay, how much we have to draw? We have to draw this value. Okay, 7.405. So you can see here, from here I have drawn a line 7.405. Then I got this point B dash and finished, because that is its actual acceleration, because it has only the radial component. Now I have to draw the the radial component of connecting rod from this point B dash. Which direction? This direction. Okay, that is either this direction or downward direction I can take, but I am taking upward direction. You can see here. So that is the direction I have taken here. Okay, so you have to take this direction. How much I have to draw? You can see here it is 0.965. So it will be very small. So you can draw near to 1 centimeter. So you can draw that in that direction. You got the mark the point as x dash, since it is a radial component. And from here you have to draw the tangential component. Length you don't know, because we don't have the angular acceleration. So what we will do is, from here draw a line which is perpendicular. So from here draw a line which is perpendicular to unknown length. We don't know the length. So just keep on extending up. Okay. So if we finish that, then now we have to draw the acceleration for the piston. So here also, like in velocity, acceleration, since the piston can move only in this linear path, there is no radial component and there is no tangential component. It has only the absolute acceleration. Okay, so this is the direction in which the piston can accelerate. So from where we have to start, we don't have an end point here initially. So we can start from the initial point fixed to point A. From here draw a line which is parallel to the direction of the this piston. Okay, so from here I will draw this. It will get joined with this line and mark that point as C dash. Now what I have to do is, now I have to join B dash and C dash in order to get the acceleration for link the link connecting rod. So we can find out the acceleration of the all links from this diagram. This is the acceleration of crank. This is the acceleration of connecting rod. Now this will be the acceleration of piston. Okay. And these are the radial component of connecting rod. This is the tangential component of the connecting rod. Okay. Now likewise it is asked in the velocity also. We have to find out the acceleration. We have to find out the acceleration of the midpoint of the connecting rod. So here also what we will do is, same ratios we will take here also. What is the ratio? We are assuming there is a point D dash here. So B dash, D dash, this value divided by, this is what we have to find out. Okay. So that divided by the BD. So you can mark, so you can take the scale and you can mark the exact midpoint. I'll take the scale like this. Okay, since this is 12 mm, so midpoint will be somewhere here, that is 6 mm. Okay, sorry, 60 mm, that is 6 centimeter. So BD, so this is BD. So you can find here. So what is B dash D dash? This will go other side. So this value divided by B dash C dash divided by BC. What is B dash C dash? B dash C dash, this measurement you have to measure. Divided by BC. BC is this full length, that is 12 mm. Okay, so that is how we are getting 7. This I have measured, I got 7. 7 divided by 12 into this comes here, no? That is PD is nothing but the midpoint. So that is 6. 7 by 12 into 6 I got as 3.5 mm. Now what I will do is, using scale, okay, from here measure 3.5 and mark this point D dash. That is how we are getting this value, that is the midpoint of the acceleration of the midpoint. Okay, I got that point. From here now what you have to do is join A dash and D dash. Now that will be the acceleration of the midpoint of the connecting rod. Here what is the value of acceleration? Here it is this length. Okay, So in order to find out that AD, acceleration of the midpoint D, is equal to A dash D dash. This is in the value we are getting from the diagram, and you have to convert into the scale. Okay, scale is nothing but, since we have divide by 20, multiply by 20, 4.4 is the value of measurement of this one. That into the 20 is, I'm getting it as 88 meter per second square. So that is the acceleration of the midpoint, okay, of the connecting rod. So we have got a lot of values which is required and also which is not required, but we will take down the value which is required. This value we require, that is the tangential acceleration of the connecting rod, A T of C given B. It is equal to 6.9 is the value which I am getting. I will show you here. Okay, so that is nothing but this value, this measurement value of the acceleration diagram, AT of C given B. AT of C given B is equal to 6.9 into scale. Scale is nothing but 20. So you get the value 138 meter per second square. So just keep it over there. We'll take whenever we require. And I have again shown you the acceleration of midpoint of connecting rod. So that is nothing but we have already done. Now we will go to the second part of the question, that is we have to find out the angular velocity of the connecting rod. What is the formula for angular velocity? Is nothing but omega BC. BC is the connecting rod. Omega of BC is nothing but the velocity divided by its link length. Okay, so that is velocity is 3.4, which we got from the velocity diagram, divided by its link length is 0.6 meter. So that is nothing but 5.67 radian per second square. Similarly, angular acceleration of connecting rod. What is the formula for this thing? Angular acceleration, you can see here, we have already written here. This is the tangential acceleration of the connecting rod is equal to link length into angular acceleration. So angular acceleration will be nothing but this value divided by the link length. So that is what I have given here. You can find the value here. The angular acceleration is equal to the tangential component divided by its link length. Tangential component we have already got 138 divided by 0.6. You got as 230 radian per second square. So this is the final value which we require.